All right, welcome back to the second class of Friday, everybody. So with this video, we will finish up the rest of chapter 2, which basically deals with the introduction of the concept of entropy. Okay, entropy. Probably heard it many, many times before, but maybe now will be the first time that you truly understand it. Okay, so one thing that we should remind ourselves of is that something that we've shown throughout this chapter so far is that large systems will roughly always be found after some long period of time in equilibrium. And equilibrium is the state, the macro state, with the greatest multiplicity of states. Okay, so this is actually roughly what the second law of thermodynamics is saying. It's saying that a system tends toward a state with the greatest multiplicity. Okay, so what we're going to do here is, since omega, the multiplicity, is usually so large, this is usually a just huge number, and we discussed how we can go between like small numbers, large numbers, very large numbers via the logarithm and the exponent. What we're going to do here is we're going to take this very large number, omega, and we're going to demote it a little bit so it's a more tangible number by using the log. And then we're going to slap on a dimensionful constant, Boltzmann's constant, and we're going to call this thing entropy. Okay? And this will be a nice variable to work with for reasons that we'll see more as we continue to work with it. But just for now, this is just the definition of entropy, and we'll usually use the letter S to define it. Okay, so what is what is the value for the entropy for an average object? Well, one thing we could do is we could take an Einstein solid. So Einstein solid, what did we find before? Well, we found that the microstate function looks like this. And that's when Q is much greater than N, the so-called thermodynamic limit, if you remember. Okay, well, all we do is we take the Boltzmann constant times the logarithm of omega. And what do we get? Well, let's go through it. E times Q over N to the N. Remember that since there's an exponent within the logarithm, we can just pull it outside. So this is N times K times ln of EQ all over N. Now we can, break this up a little bit. So we can write this as N times K times ln of Q over N plus ln of E. And obviously, ln of E is just 1, because E to the 1 is E. So we have that the entropy for an Einstein solid looks like N times K times the quantity log of the number of units of energy over the number of oscillators plus 1. Okay, so just to get a ballpark figure for a number that's relevant to systems that we can actually think about, let's take N to be 10 to the 22, I think I put in. Q to be 10 to the 24, so 10 to the 24 units of energy, 10 to the 23 oscillators. If you put these in, you get a number that looks like this. So something on the order of 1. And the units there are joules per Kelvin because of the fact that we're using Boltzmann's constant here. And Boltzmann's constant has units of joules per Kelvin, and the microstate, the multiplicity function, is unitless, of course. Okay. So just a little note here. So we see that entropy is directly related to the number, the multiplicity, or the number of states corresponding to a specific macro state, right? So you've probably heard that but like entropy is like related to the disorder of a system, right? Because like the more disordered it is, the higher its multiplicity function is, because there are just more states that look disordered. And this is actually a pretty good way to think about it, but I would just personally caution you, and I would really, really stay close to the idea of thinking of entropy just in terms of counting the number of microstates. There are some ways where this can get you into a little bit of trouble. Okay, so this is just a little note I wanted to put on here. So it's related to disorder, but stay close to its proportionality to log of omega. You always think about that, you won't go wrong. Okay? Well, if you do go wrong, you'll have made a mistake, but you won't misunderstand the concept. All right. So let's just flesh out some simple properties of entropy. It'll be additive. So if we take the total entropy, okay, ln omega of some system that's split up into a bunch of subsystems, well, we know that omega total is arrived at for a total system just by taking its subsystems and multiplying the multiplicities together. But then just using the property of the log that we've discussed, you can take this and break it up, and you get the following. But then these are just specific definitions of entropy themselves for systems A and system B. So you see that the total entropy of the system is pretty nice. It's just the entropy of A plus the entropy of B. Let's see. Okay. So yeah, I guess at this point, we could restate the second law that we just cited on the other page with entropy substitute for microstates, because we were talking about systems tending toward the state with the most number of microstates, or the biggest multiplicity. But we see that entropy is just defined as being proportional to the multiplicity. So you can rephrase the second law in terms of entropy. Yeah, that's all I wanted to say there. Would have liked to have asked anybody if they had any examples of the second law in terms of entropy in their real lives, but there's nobody to talk to right now. So I'll give an example. So basically, I mean, the second law is saying that entropy, on average, it always increases, right? It means that a system tends toward the state with the most number of microstates, which means it has greater entropy. But there are situations in your lives and mine where it seems like you're always lowering the entropy, right? So like, for example, cleaning your living space. Like if you live, let's say you've got your bedroom and you have your dirty clothes and you clean them and you hang them up. If you're a messy person, maybe your clothes were strewn about your room. That's a state with high entropy, right? Because there's more numbers of ways for your clothes to be strewn about your room than there are for them to be not. So that would be a state of high entropy. But when you clean them and you fold them up and you hang them up or put them away, you're lowering the entropy, right? So you might take issue with the second law of thermodynamics because you're saying, well, it says that entropy can like basically never decrease, but I have direct examples of it. So if you think that, you basically just need to look a little bit more closely at the system, because, for example, for the case of like you doing this cleaning in your house, you have to also include yourself in the system. So the food that goes into you is being metabolized and stuff's being converted into heat. Ultimately, if you take all of those processes into account, like the actual washing, like using the washing machine, moving the air molecules around as you're doing this motion, you take account for all of the changes in entropy, what you'll find is that it actually does increase roughly all the time. There are some interesting cases where it might even appear that you might be able to break the second law of thermodynamics. And this is what's called Maxwell's demon. Maybe you've heard of this, this thought experiment before. And I was doing just a little bit of research on this. And apparently, when I think Maxwell said this originally, he did not mean demon in the sense of like an evil creature or being or something that is doing the stuff that we're going to describe, but he meant it in the sense of like something that is just mediating a process. So that was just an interesting tidbit. But basically what Maxwell's demon is supposed to be is it's some kind of sentient being that has the following. So, well, yeah, it's got, picture this dotted line as like a shutter that can just like be closed or it can be open. And there's some kind of little person here who is able to close and open it based on some things that we're going to describe. So you've got gas flying around in here all over the place. These things are just moving all over. Different molecules have different energies. So if the being sits there and lets the system come to equilibrium, let's just say that initially it started off with system A being hot and system B, this side, being cold, comes to equilibrium, it's now in a state of high entropy, right? Because the second law says that entropy can only increase. The thought experiment that is Maxwell's demon is, suppose that either some highly advanced civilization or some kind of weird physical process is able to give rise to the following mechanism, where effectively you have some kind of intelligence that can detect when something is moving faster than the average molecule in here and either stop it from going through this shutter right here so it can close it off so it stays over on this side, or it can let it through so it goes to the other side. So effectively a mechanism so that you can sort these molecules by their kinetic energy, by how fast they're moving. So if you could do that, you could actually open and close this according to what's coming your way when. And you could sort, like, say, the colder pieces on this side, you could sort the hotter pieces on this side, and you would have decreased the entropy. So this is kind of an interesting situation to look at, and it gets pretty deep pretty fast. So there's still lots of arguments about this, about whether it's even possible to have some kind of being that can actually do this. But there are also apparently arguments where showing that in order to actually carry out this process of reducing the entropy, if you include the little being or intelligence or whatever, in order to actually measure the speeds of all of these molecules and then account for how fast they're moving toward it and do all those computations, that the increase in entropy due to the being having to do all those computations will offset the decrease in entropy of the overall decrease in the system. So this is just something interesting to think about. Maybe you can find some stuff online if you want to and read about it, and we can chat about it sometime in the future. But I just thought I'd mention this because it's fun to think about. All right, so now let's get into calculating the entropy of an ideal gas. So all right, well, we had just earlier today, we wrote down what the multiplicity function looks like for an ideal gas in the large N limit, and it looked like the following. All right, hopefully I didn't make any mistakes there. So if we have the multiplicity function, we can take Boltzmann constant and then take the log of the multiplicity function, and we've got our entropy. Okay? So using the same approximation now, we can rewrite, we don't need to do that. We can just rewrite the entropy using this formula right here. And using some of the same approximations that we used to get this, like the large n limit and whatnot, we can rewrite this entropy as the following. Oh, there should be a parenthesis there. And this is called the Sackur-Tetrode equation. I think that this name might be French, might have a different pronunciation, but doesn't really matter for the moment. Okay, so yeah, part of your homework is actually showing exactly how this works out and going from here to here. So that's why I'm not going through a whole lot of steps. So for now, let's take helium. And specifically, let's take 1 mole. Let's take the temperature to be about room temperature, so like 293 Kelvin. And let's also take pressure to be just the usual atmospheric pressure, just on the surface of the Earth. So, ideal gas law summoned, we have nRT over P. So the volume corresponding to this arrangement here should be 0.025 meters cubed. And using the equipetition result, we can solve for the energy, and that is 3,700 joules. So now if we take all of this, we throw it in for our entropy, and we also put in the mass of helium into here, we can find that the entropy for helium under these assumptions is going to be the following. So it's going to be n times k times 15.2, and then if we work all that out, we'd get 9.1 times 10 to the 24 times k, Boltzmann constant. Boltzmann constant is really, really small, so it changes this huge number into a smaller number, so we get something that looks like 126 joules per Kelvin. Okay, so this is a typical entropy for an ideal gas like helium under like room temperature and pressure and a decent number of molecules. So in general, what should we notice about all of this? Well, we should notice that we increase the volume, or if we increase the energy, or increase the number of particles, if we do any of these things, then the entropy should go up. Okay? So we can get that kind of scaling by looking at this, and just seeing how it scales with respect to V, U, and N. It's always useful to work out these kinds of scaling relations. Okay, so let's work with a specific case right now. So let's fix the volume. Let's fix everything but the volume, and look at what the change in entropy looks like. So if we fix the volume, sorry, why do I keep saying that? Fix everything but the volume. Then for the ideal gas change in entropy, so if we calculate SF minus SI, and we're only changing the volume, one can show that this will just give the following. N times K times ln of Vf minus ln of Vi. And the reason this simplifies down so much is because we're considering the difference of the entropy, not the entropy itself. And so all of this gobbledygook in here just kind of disappears because we're just concerned with the difference here. And so we can write this as n times k log of Vf over Vi. And we'll note that this is for U and N fixed. So we should think about whether this makes sense, just via our intuition. So if we were to consider an expansion, so let's consider Vf greater than Vi. Well, then the change in entropy is positive. So it's greater than 0, right? This will be positive because Vf is greater than Vi. So we know that since we're keeping everything fixed, that this is going to be what we've called in the past an isothermal expansion, right? Because we're keeping the energy or the temperature fixed. And we know that if we want to expand something isothermally, that heat has to actually enter in order to keep the temperature the change, keep the temperature the same, right? So in this case, we can think of the entry of heat, which you should think of as like a random motion of molecules, particles, whatever. We should think of heat as literally being the reason that this entropy is increasing, because heat is kind of like a form of randomness. It enters the system becomes more random, the entropy increases. So this makes sense, and it gives us an understanding of how heat contributes to the entropy. All right. Now let's consider a different situation. Let's consider gas expansion, but not in the usual way. We'll just consider it via a hole. So what I mean by that, so let's start with a cylinder or something like this. And let's say, well, let's say this is sealed off initially, and you've just got gas in here. Okay, nothing in here, gas in there. So if you poke a hole right here, boop, then obviously these molecules are going to eventually shoot their way through, and given enough time, the molecules will distribute themselves throughout the entire system. So one thing we should note about this is that the work done on the gas is 0, right? Because we're not actually doing anything. It's not being it's not being like forced to go into here. It's just following its own usual random motion, and it winds up in there after some period of time. So the work done is 0. There's no heat being added or taken out, and the change in internal energy is obviously 0 because we're assuming that all the collisions in here are conserving energy. But the entropy still increases. And we already understand why that is, right? When we were talking about the microstate counting for ideal gases, we were talking about how there are more microstates if you have a bigger volume, right? Because there are just more spots for the molecules to find themselves. So since there are more microstates, once the whole thing has spread out, then there must be more entropy, right? So this is just an interesting example of how you can increase entropy but not have to do any work, not have to do any heat, not have to change the energy at all. Okay, now let's talk about the idea of so-called entropy of mixing. So the idea is just that entropy increases when two things mix. So S goes up when mixing occurs between like unique particles or constituents or something. So a typical example could be like coffee and cream, right? So what happens here is that like, you start off with a cup of coffee, and separately, I don't know, like not a cup of cream, obviously, but let's say a shot of cream. That's about how much you would actually have. So initially it's really ordered, right? Like the coffee is all in one part of the system, the cream is all in the other part of the system. But then once you add them, you add them together, you give it enough time, and they completely distribute themselves, right? So, and they mix. And obviously, the reason that this happens, they're coming to a sort of equilibrium, right? They're exchanging particles, and they're ending up in a more disordered state. More disordered or more entropy. And there are lots of other examples of this that you could think of. So how could we calculate what the entropy of actually just mixing is? So to do that, let's consider system broken up into A and system B. Got stuff on one side, got something different on the other side. Let's say that they have the same number of particles, they have the same volume, and they have the same energy. So we could poke holes, one there, and we could just wait for them to mix together. So if we take our camera and we just think about watching system A while this happens, while it expands, it goes from being in this volume to subtending a volume that encompasses this whole region. So its volume increases. And if we look at system B as well, the mirror thing happens. It extends from the volume of B, which they're the same volumes, but each of them doubles their volume effectively, right? So we should expect that the entropy should increase. So what we can do is we can calculate separately the entropy of A, and since they're the same, I mean, they're increasing in the same volume, it's going to be equal to the change in the entropy of B. And this will just be Nk times ln of Vf over Vi. So it's just like the example we had said before where everything else is held constant because all of these things are held constant while this is happening. So now all that's happening is we know what Vf is in terms of Vi. So if it increases by 2, then we just have Nk times ln of 2Vi over Vi. Vi's cancel out, and you are just left with Nk ln of 2. So if you do this 2 times, so we know that the total entropy, as we had just shown before, is going to be the change in A plus the change in B, but they're the same. So 2nk ln of 2 is the entropy of mixing for this case. This is literally just the entropy change that is due to the two systems spreading out and mixing with each other. And note that this is only going to be the case if these particles are distinguishable, right? If they're indistinguishable and you poke holes here, well, you can't tell that the stuff that was over in A is now in the part B because they look exactly the same. So note the difference between distinguishable and indistinguishable here. All right, so here's another nice way to look at the entropy of mixing. So let's consider we have, let's consider a chamber with 1 mole of helium. So we know how to write the entropy. It's just this big, ugly expression. It's actually not even that ugly. It's much worse. 4 pi mu over 3n h squared 3 halves plus 5 halves, and I always leave that off. Okay, so this is how our system starts with 1 mole of helium, and we can calculate the entropy as such. So if we then take a mole of argon, which is obviously going to be distinguishable from helium, they're different molecules, and add that, so if you 1 mole argon. Then S total is just going to be the entropy of helium plus the entropy of argon. And let's just say that the argon that you're putting in, like we'll just assume that basically the masses of helium and argon aren't actually that different, that we can approximately write this as just 2 times the entropy of helium. So if we have distinguishable particles here, it just becomes what you would think it would be. It would just be 2 times whatever the original entropy was. But what happens if instead of adding argon, we just add another mole of helium? Okay, so add 1 mole of helium instead of adding the argon, not after adding the argon. So if we do that, well, we just have our equation up here, and we just take all of the variables and we just send them to 2 times themselves, right? So we would have that S total is equal to 2n, because now there are 2n particles. That's my cat meowing into the void, if you can hear that. Times ln. Oh my god, Rudy. 2n times 4 pi m 2u, 3 times 2n h squared, 3 halves plus 5 halves. So what do we see? Well, we see that these factor of 2's in here just completely cancel out. And we just get something that looks like this. So if we use the properties of logs to rewrite this a little bit, we could show that this is just 2 times the original entropy of the helium. But now, because of this 1/2 factor in here, you actually have to subtract 2 times n k ln of 2. And this is exactly the entropy of mixing term that we just showed before. So this is the entropy that you don't get because you didn't put in something that was unique. And this, I always found this kind of confusing, but hopefully this is making sense. If you have questions, shoot me an email. So this is the piece of entropy that you do not get because you're putting in an extra mole of the exact same thing, and so they're indistinguishable from each other. So there's no actual mixing occurring. You only get this entropy of mixing when you have distinguishable particles that are mixing together. So in this case, it actually gets subtracted off of what you would originally think the actual entropy should be. Okay. So yeah, it's important to realize that this comes about because our formula for S here, it actually accounts for indistinguishable particles. Well, what if we hadn't done this? So if we hadn't done this, we would have a formula that looks like the following. It would look like nk times ln of v. There would be no over n term there. 4 pi mu. And really, it's all the same from there on. It's just that one n that gets left off. And I forgot it again. So this would be if they were actually distinguishable. Like if you could distinguish the first mole of helium from the second mole of helium. And this leads to some really weird results. So basically, you can show that if you take this formula and you take a box and you've got molecules flying around all over the place, that you could actually decrease the entropy of the entire system simply by dividing it up. Just putting a barrier there. So if reality worked like this, if you could literally decrease entropy just by dividing up systems of like helium is on this side and helium is on this side, that would be a very, very weird world. So this is kind of a lesson in telling you to take very seriously the fact that, so like the different molecules of helium are literally indistinguishable from each other. There is no way to tell them apart. So you can't actually do anything like this in real life and decrease entropy overall. It would break the second law. You can just go around just dividing up systems in your head, and all of a sudden it's got less entropy than it started with. Like that is utter nonsense. So this is just a lesson in why that's the case. So yeah, I think that's actually about it. Just wanted to say that basically we can rewrite what we mean by irreversible and reversible at this point. So irreversible processes, we've talked about this a lot in terms of microstates. Now we can just say that these are processes where the entropy increases. And since entropy doesn't tend to decrease, this is why they're called irreversible. And this is just the exact same statement with, oh, I should put increases. This is the exact same statement as the statement about microstate counting. It's just cast in the language of entropy now. And reversible processes are processes which do not change the entropy and thus can be reversed no problem, because there's no asymmetric like probability distribution for stuff like this. All right, so that is everything from chapter 2. Good job, everybody. We made it through yet another chapter. So yeah, we will start chapter 3 next week, and hopefully your weekend goes well and you're able to get the homework finished up. And if you have any questions, just don't hesitate to shoot me an email. I will try to keep my inbox open as much as possible. Okay? Goodbye for now.